Okay, so this is the 14th lecture in my series on algebraic number theory. This lecture is primarily aimed at only really proving one proposition, which links the minimal polynomial of an element to whether it's integral or not. So, overview is going to be pretty brief. We're only really going to do one thing. We prove a proposition linking the integrality of an element to the coefficients of its minimal polynomial. Okay, so this kind of, I guess this is going to ultimately answer kind of a natural question you might have. So I'll go ahead and state the proposition. This is going to be 14.1. Proposition. So I'm going to let A be an integrally closed integral domain. So this is important condition. Integrally closed integral domain, and let's say I have field of fractions K. Okay, and let's say I have a field extension, let L containing K be a field extension. Okay, now so the proposition basically tells me how do I check if alpha in L is integral over A. So then alpha in L is integral over A. Alpha in L is integral over A if and only if the minimal polynomial of alpha over L. So I guess first you need to know that alpha is algebraic. So if I'm being careful, alpha is algebraic. Over L, and the minimal polynomial of alpha of x lies not only in K of x but in A join x. So the coefficients are in A, and this minimal polynomial, I should be more specific, where alpha x is the minimal polynomial of alpha over K, the field of fractions. Okay, so essentially, I guess there are a couple different ways to look at this. One is it says, okay, to check if an element is integral, I just have to compute its minimal polynomial. Another way to view this is like, so I mean the definition of being integral over A means that it satisfies a polynomial. We know that every, alpha is definitely going to satisfy if it satisfies a polynomial with coefficients in a, we know that every element is going to satisfy its minimal polynomial just based on the definition of the minimal polynomial. So what this means is that I really only have to check that basically, well, maybe I'm just kind of repeating myself at this point. I really only have to check that the minimal polynomial has coefficients in a. Okay, so we'll talk about the proof, and then we'll talk about this. Why is there this integrally closed conditions? It turns out it's, if you think about it for a few seconds, you'll see that this is really like a necessary condition. Okay. So let's prove the result. One direction of this if and only if is trivial. Clearly, if main alpha of x is in A joint x, then alpha is integral over A this is because since min alpha of x, this is a monic polynomial, it is monic. Okay, so the other direction is the hard part. So suppose now okay, and now we're going to have to do a bit of work. So now, oh sorry, no, I've got this flipped. Okay, suppose now alpha is integral over A. Okay, so I know it satisfies some polynomial with coefficients in A. I have to show that the minimal polynomial necessarily has coefficients in A. Okay. So the first thing to notice is that, I guess, first observe the following. I see. Okay, first observe that if alpha prime is another root of, let's say, min alpha of x, then I want to say alpha prime is also integral over A. Let me see. I'm worried that maybe I'm missing some hypothesis. I guess it's not going to hurt really if I assume L is finite. Do I need this though? Okay, let's keep working and see if I actually end up using that. That was funny. Okay, so this is my, maybe let's not say observe. Let's first I claim. Okay, so to see this, essentially we use the following. There are two pieces to this. One is we have isomorphisms K join alpha isomorphic to K join X mod. And I should tell you what these are isomorphisms of. These are isomorphisms of A modules. K join alpha is K join X mod and alpha of X. Yeah, which is isomorphic to K join alpha prime. Since any root of this minimal polynomial, all these all the roots of this minimal polynomial have the same minimal polynomial. You can check that you have an isomorphism here. If you want to go this way, you'd send x to alpha prime. I guess technically it'd be x plus min alpha of x maps to alpha prime, and you similarly send it here to alpha. Okay. And you can check these are isomorphisms. This is kind of like an important ring theory fact. Okay, now, what can I say about K join alpha and K join alpha prime? Well, since basically we want to use one of Dedekind's criterions of integrality. Or maybe with I think so. The issue is here, right? So initially, I want to say, okay, this is finitely generated, so this is finitely generated as A modules. Therefore, alpha and alpha prime are algebraic or integral. However, we run into a bit of an issue, right? In that Dedekind's criterion really needs these to be A's and not K's. I don't think we can circumvent that, so we kind of need to be a little bit more clever with how we do this. So I'm gonna say let alpha satisfy let's say alpha to the n plus c n minus 1 alpha to the n minus 1 plus c not equals 0. Okay, with these ci's in A. Okay, then if we call this isomorphism of pure sigma, so I've got this isomorphism sigma here. Consider what happens when I apply sigma to the whole thing. Sigma of this thing. Consider what happens when we apply sigma. Well, the first thing to notice is that this isomorphism here actually, basically, it sends alpha to alpha prime, and it fixes K. So what does that mean? Since sigma fixes K, sigma is A. I guess one way to say this is sigma is a K vector space homomorphism. I guess even stronger, a K algebra homomorphism. Okay, so I could have completed something stronger here and said K algebra. Since sigma is a K algebra homomorphism, when I plug in alpha prime to this thing, plus c to the n minus 1, or maybe I'll do this more carefully here. Sigma of the whole thing, well, it's going to be 0 since it's 0 on the left, sigma of 0 is 0. It's going to be sigma of alpha to the n plus c to the n minus 1, alpha to the n minus 1 plus c naught, which is then, okay, using the algebra homomorphism properties, it's going to be sigma of alpha to the n plus cn minus 1. Since this lives in k, it can pop right out. It'll be sigma of alpha to the n minus 1 plus sigma of c naught, which is just c naught. Okay, and sigma takes alpha to alpha prime, so I see that alpha prime also satisfies the same thing. Okay. When I plug in alpha prime to this polynomial with coefficients in a, I also get 0. Okay. Thus, alpha prime is also integral over a. Okay, so what does this tell me? It tells me that all the roots of alpha prime are, or all the roots of the minimal polynomial of alpha are an integral over a. So moral, yes, all the roots of alpha of x are integral over a. Now, what can we say about the coefficients here? The coefficients are, so the coefficients so there are definitely elements of k. The elements of k because it's the definition of the minimal polynomial. It's the minimal polynomial of alpha over k, so it has coefficients in k. 2, the coefficients are symmetric polynomials in the roots. Okay, so see lecture 10 for this, if this is unfamiliar. And thus also integral. So the coefficients are some multiplication and addition of integral things, are therefore integral because integral elements form a ring. Sorry, this should be over a, not over k. Over a. Okay, and what do I see now? There are elements of k which are integral over a, 1 and 2 together with integrally closed hypothesis. This implies man alpha of x has coefficients in a. As desired. Okay. So what did we use here? The most useful fact was this thing here. that we had isomorphism of K algebras. Okay. And that allowed us to show that the roots of the minimal polynomial were all integral, therefore the coefficients had to be in A because A is integrally closed. Now, one final remark, so just thinking about, can I relax this condition integrally closed? And the answer is basically, the answer is 100% no. Remark, so this is 14.2. Remark. Note, if A is not integrally closed, and alpha is in K, integral over A, but not in A, well then the minimal polynomial, so essentially I'm taking L equals K in this proposition 14.1, this guy, this minimal polynomial is just x minus alpha, does not have coefficients in A, despite alpha being integral. Over A. Okay, so this is kind of like an integral domain is integrally closed if and only if the minimal polynomial of every integral element over a field extension of L, or a field extension of the field of fractions, has coefficients in A. It's kind of a complicated statement. I don't imagine it's super useful, but I guess it's better to think of it as this integrally closed condition is definitely necessary for the theorem to hold. The other thing is, when I initially wrote these notes, I just assumed L was finite over K, but I think, L doesn't necessarily have to be finite over K. You can just kind of think about, well, if alpha is integral over A, then it lives in some finite extension, so you can kind of always reduce to that case. Okay. That about wraps this lecture up.